Good evening, Fiveable. Shane here for AP Statistics on Fiveable, the platform that will help you get a 5 on your AP exam, save you tons of money and time, and just better as a human, especially when it comes to statistics. One of the most important topics to come away with. And I do feel like if we had more citizens who were AP stats trained or stats trained, we'd be in a much better place. So like I said, my name is Shane. I'll be running you through this year for AP Stats. I'm working on an Instagram, just kind of figuring out the kinks of it. So you can follow me, Stats with Shane. There's not a lot of content up yet, but I kind of have planned out what the rest of the year will look like on that platform. So you can go ahead and follow me there as well. So we're going to dive into it like we always do, with just kind of a schedule of what's coming ahead. I go live Thursdays at 5 p.m. Eastern Standard Time or 5 p.m. Pacific Standard Time, which is where I'm in. I'm in Oakland, California. The next major topics are going to be sampling distributions for proportions and means. And then we're going to cover confidence intervals. So those are the three things I have coming up in my class, as well as most classes. I go to trainings about 2 or 3 times a year for different AP teachers around the world, and I get to see, well, mostly around the US. I get to see where they're at, and this is usually the scope of sequence of AP stats in this country. So here are kind of the things you're going to get from me in this live session. You're going to get exam tips. You're going to get FRQs and multiple choice questions. Most important, calculator tips. A lot of students use this to save time on the AP exam, which is one of the struggles, especially on that free response part. And just about a bunch of other stuff. I've been teaching this for 4 years, so I have a good idea of the tips and tricks that you're going to need to do well and score a 5 on the AP exam. Okay, so here's kind of a rundown of the agenda that we're going to go through. So we're going to go over what is a binomial setting and distributions. What the heck is bins? We're going to look at the binomial formula, kind of break that down. Why is the formula the way it is? We're also going to look at the binomial distribution for the mean and standard deviation. So how do we find the average and standard deviation of a binomial distribution? Then we're going to look at geometric. So geometric is very similar to binomial, except for one key difference. And we're going to look at the formula as well, do some expected value. After all this, I'll go over some practice problems. There's a really famous problem from 2016 that I will go over with y'all. And then if we have time, I'll go over some practice problems as well, multiple choice, show you a pretty key handout that you guys can take with you and use later. So without further ado, let's dive into it. So what exactly is a binomial setting? Where a binomial setting is when we count the number of times an outcome occurs in a fixed number of trials. So that's a binomial random variable. So again, we have a fixed number of trials and we count the number of times an outcome occurs. For example, if I was flipping a coin 5 times and I wanted to count how many heads came up. So we call that a binomial random variable. And we'll figure out why that's called a binomial random variable on the next slide. A binomial setting occurs when we perform several independent trials of the same chance process and record the number of times a particular outcome occurs. So if I wanted to say a binomial setting could be flipping a coin 5 times and counting the number of, not counting the number, saying I want to know out of 5 coin flips, what's the probability I get 2 heads? Right, so there's a fixed number of trials, each trial is independent, and I'm looking for a specific outcome. So that's kind of binomial random variable versus setting. Now we're going to dive into it a little bit more with this thing called bins. So the way you know something is a binomial setting is if, excuse me one second. Oh, let me get out of that. Bring this back up. Uh-oh. Let me bring this back up. Not sure what happened. There it is. Some technical difficulties. Why is this not coming up? Let's try another one. Oh, there we go. It was just up. Sorry about this. Come on, we're almost there. Let's go. There we go. No, sorry guys. For some reason it's the internet, but it's not loading. Let's see. Come on. This is very weird. Let's exit that. It wants to come up. Come on, come on, come on. There we go. Okay. Let's present there. This is kind of ridiculous. Come on, internet. Technology is great when it works. You know what? Let me see if we can just go. Oh, there we go. Okay. There we go. Sorry about that. So, bins. What exactly is bins? So, bins is a way that we can tell if something is a binomial setting. So, four easy letters to help us with a binomial setting. So, the first one is it binary? Each child needs to have a success or a failure. For example, in our coin flip that we talked about earlier, a success would be getting a heads. Failure would be getting a tails. So binary. Next one, independent. So we need to make sure that each child is independent from the next. Going back to the coin flip, if my first flip is a heads, that is not going to affect my next flip because a coin is independent and it doesn't have a memory, so it's not going to remember what happened before. The N in bins is number of trials. So the number of trials must be fixed. You must say, we're going to do this 5 times. We're going to do this 10 times. Whatever it is, it must be a fixed trial. Next is the success. So each trial must have the same probability of success. So again, each trial needs to have the same probability of success. Flipping a coin, every time I flip a coin, I have a 50% chance of getting a heads, as long as it's a fair coin. So bins is a good checklist for you to do to understand if something is a binomial setting. Here's an example. Let's say we have the probability of a pair of parents having a child with blood type O is 0.25. If a couple has 5 kids, what is the probability that exactly 2 kids will have blood type O? All right, so let's check this. First, is it binary? Yeah, you either have blood type O or you don't. Success or failure. Is it independent? Yeah, each child is independent of the next. So we don't need to, having a boy the first time or having someone with blood type O the first time isn't going to affect the next one. Number of trials. Is there a fixed number of trials? Yeah, it's the 5 kids, right? We're only going to have 5 kids. same rate of success. Do you have the same rate of success? Yep, each kid has a 0.25% chance of having blood type O. So this would be a binomial setting. So what's the formula look like? Here's the formula. It looks a lot more complicated than it actually is. So let me break it down for you. First, we have the probability of some outcome happening is equal to all the combinations times the probability of success to the power of how many successes do you want, times Q, which represents the probability of failure, to the power of how many failures you want. So let's break it down a little bit more. So this first part right here in parentheses, that allows you to create all the different combinations. So because we really don't care if let's go back to our child example. If the first child was blood type O and the second child was blood type O, that's great. We have 2 kids, that counts. Doesn't matter if the last 2, first 2, whatever. So what we have to account for is all the different ways we can get 2 kids with blood type O. The way we do that is we use this formula up here. So we do n factorial, which means the number times all the numbers below it up to 1, divided by n minus x. Remember, n is the number of trials. So n minus x would be the number of failures, factorial, times the number of successes, factorial. And that formula will give you all the different combinations. P is the rate of success. So 0.25 was our rate of success. To the power of x, we wanted 2 kids, so we would put 2 there. Times Q, which is the rate of failure. So 0.75 to the power of n minus x, which is just the number of failures, right? If I have 5 kids, 2 of them, and the number of successes I want is 2, then we're going to do 5 minus 2, which gives me 3. So that's the number of failures, right? If I have 2 kids with blood type O, then I have 3 kids without blood type O. That's the formula. I'm going to show you a really easy way to do it on your TI 83 or 84. Super, super quick. All right, so let's go back to our example. It's the probability of getting blood type O. So because there are 10 ways to get children with 2 children with blood type O in a group of 5, we do the probability of getting exactly 2 is 10 times 0.25 to the power of 2 times 0.75 to the power of 3. And doing that on my calculator, we get 10 times 0.25 to the power of 2 times 0.75 to the power of 3. We get 0.2636. So about a 26% chance of getting exactly 2 kids with blood type O if I have 5 kids and each kid's probability of getting blood type O is 0.25. Mean and standard deviation. So in a probability or in a binomial distribution, you will have a mean and standard deviation. They're really easy to get. Here are the 2 formulas that you need. The average of a binomial distribution is going to be your number of trials times the probability of success. Your standard deviation is going to be the square root of the number of trials times the probability of success times the probability of failure. So those are the 2 formulas that will get you the mean and standard deviation of a binomial distribution. Let's take a look at our example. So in our example here, number of trials was 5. The success rate was 0.25. So the answer is going to be 5 times 0.25, which is 1.25. Standard deviation, similar thing. Square root of n times p times q, where n is the number of trials. We had 5 kids, that's our number of trials. P is the rate of success. So we had a 0.25 rate of success. And Q is the rate of failure. So we're going to have 0.75 as our rate of failure because failure is going to be 1 minus success. And that gets us 0.96. So that'll be the standard deviation, and your mean will be 1.25. All right, so that's all I got for geometric or binomial, but we'll come back to it and do some examples on the calculator. Geometric. So geometric is very, very similar. The only difference in geometric is that we're repeating, we're looking for our first success. So we want to know what's the probability that my third kid is the first kid with blood type O. So again, we're looking for the probability that my success comes on this trial, my first success, I should say. So geometric setting is the repeated chance behavior until a success occurs, right? So flipping a coin, and the probability that your first heads is the third flip or the fourth flip. That's a geometric setting. It's very similar to a binomial, but you do not need the fixed number of trials. So you still need the binary, success, failure. You still need independence. You still need the same rate of success, but you do not need the fixed number of trials because you're trying to figure out when the first success or the probability that the first success falls on this trial. Here's the formula for it. So the probability of getting your first success on, let's say, K, the fourth or fifth, it doesn't matter, would be 1 minus the probability of success to the power of the trial number you want success on minus 1 times the probability of success. So to break that down for you, if we were to figure out what's the probability that the first kid who has blood type O is the fourth child, you would do 1 minus 0.25 to the power of 4 minus 1, which is 3, times the probability of success, which is 0.25. And here's where that formula comes from. If my first kid has blood type O on trial 4, that means the first 3 had something other than blood type O. And we know the probability of having something other than blood type O is 0.75. Because each trial is independent, I can use the general multiplication rule to figure out that probability. So the probability that my first child is not blood type O is 0.75. To get the probability that my first and second, I would just multiply 0.75 times 0.75. And then the third, I would do the same, multiply by 0.75. So that would be that the first 3 babies born do not have blood type O. Because they're independent, I can just do their probabilities of failure multiplying each other. Then the probability of success, because the fourth one was blood type O, so I would multiply that by 0.25. We'll do some examples. Stats, the best way to learn it is to do it. The mean or expected value of a geometric random variable is super easy. All it is 1 divided by the probability of success. Okay, so 1 divided by 0.25 is going to be 4. So the expected first success is on the fourth trial. All right, we're still waiting for people to join, so we'll jump into the free response question. But before I do that, let me show you an item that I think might be helpful for you. So if you look here, I've kind of laid out the different probabilities or properties, I should say. So binomial, we have that bins right here, where this is the n fixed number of trials. The probability of an outcome is consistent, so the same rate of success, only 2 outcomes, so binary, and independent trials. Over here, all I need is those 3. I do not need the fourth one, which is the fixed number of trials. Right. Here are the 2 formulas. You don't need to worry about this. Here's your expected value. Here's your standard deviation, expected value. Now here's the key part of this, is right here, the TI-84. And the reason you're seeing pi is just because they used pi as the symbol for the probability of success. We use p. All right. So when you're doing it on your TI for a single event, for binomial, for example, to get the probability that 2 kids out of 5 have blood type O, we would use binomial PDF n times p times k. I'm going to change this to p as to not confuse us. So that's to get the exact probability. To get the cumulative, so what's the probability that 1 or 2 kids, with 0, 1, or 2 kids have blood type O, you would use CDF. And very similar for our geometric. Again, this is P, and this is the number of trial you want, so the success. But let's get into some examples. Let's look at our first example. Assume that 40% of the market prefers Pepsi. What is the probability that 5 out of 10 randomly selected Coca-Cola drinkers would choose Pepsi in a blind taste test? So again, this part right here is all the different ways we can get 5 out of 10 people to choose Pepsi. Maybe it's the first 5, maybe it's the last 5, maybe it's the middle 5, but we have to take that into account. This part right here is getting 5 people to choose Pepsi. This part right here is getting 5 people not to choose Pepsi, which will give us 20% chance. Now using our calculator, we would type in that, but let me show you using my calculator. You're going to go to second distribution right there. Go down to binom, PDF. Number of trials, 5. The number of success. Success, remember, is picking Pepsi, 0.4. Oh, sorry, trials is 10. I'm sorry. Probability is 0.4. And the X value is the number of successes that you want. We want 5. We're going to enter that. Look at that. We got 20%. Going over here, just to show you how similar it is, geometric and binomial. We have assume 40% of the market prefers Pepsi. What is the probability that the first cola drinker to randomly select Pepsi in a blind taste test would be the 5th person? So if it's going to be the 5th person, that means 4 of them had to fail and 1 of them had to succeed. So the probability that the first cola drinker to prefer Pepsi is on the 5th trial is going to be about 5%. And again, here's how you do it on your calculator, but let's do it together. So similar, you're going to hit second distribution. You're going to go down to geometric PDF. The p-value is probability of success, which is 0.4. When do you want your first success? That's your X value is 5. There you go, 0.0518. Now, that's all nice, but we know that the AP exam is a little bit harder than that. So let's take a look at our 2016 question. Okay, so it says a company manufactures model rockets that require igniters to launch. Once an igniter is used to launch a rocket, the igniter cannot be reused. Sometimes, after an igniter fails to operate correctly, the rocket does not launch. The company estimates that the overall failure rate, defined as the percent of all igniters that fail to operate correctly, is 15%. A company engineer develops a new igniter called the super igniter. with the intent of lowering the failure rate to test the performance of superigniters. The engineer uses the following processes. Step 1. One superigniter is selected at random and used in a rocket. Step 2. If the rocket launches, another superigniter is selected at random and used in a rocket. Step 2 is repeated until the process stops. The process stops when a superigniter fails to operate correctly or 32 superigniters have successfully launched rockets, whichever comes first. Assume that the superigniter failures are independent. So that part right there is super, super important to know that the superigniters are independent. Because if it's not, then we don't have independence. And we can't do the binomial setting. So first, let's take a look and see if we actually have, well, let's read the first part, I guess, part A. If the failure rate of superigniter is 15%, what is the probability that the first 30 superigniters selected using the testing process successfully launch? Okay, so if all 30 successfully launch in a row, that means that the probability that the first 30 were successful, right, is going to be, so success is 1 minus failure. Because they're independent, I can use the general multiplication rule and put it to the 30th power. That's the probability that every single one will be successfully launched, which gives me 0.0076. So that's for part A, the probability that all 30 ignite with no problems, the first 30 in a row. Part B. Given that the first 30 superigniters successfully launch rockets, what's the probability that the first failure occurs on the 31st or 32nd superigniter if the failure rate of the superigniter is 15%? Okay, so we want to know what's the probability that the first failure occurs on the 31st or 32nd. But this part right here is important. Given the first 30 are already successful, so most students here will use geometric CDF, or PDF, I should say, and find for the 31st and then add it to the 32nd. But because the first 30 already happened, we know the first 30 already happened. So then the next launch would be the 31st, and that rate of failure is 0.15. We're going to add that to the 32nd being the first one. Well, if the 32nd is the first one, then that means the 31st was a success, and then the 32nd failed. So that probability is going to be 0.2775. So once again, because they said that the first 30 were successes, we don't care about those anymore. We want to know what's the probability that the next one fails or the 32nd is the first one to fail. We could have also used our geometric, but we would use second distribution. Go down to geometric PDF. The probability of success is 0.85. We want to know what's the probability that one fails on the first one. 0.15. 15%. We're going to add that to the probability that the second one fails. So that plus 0.15 gets me 0.2775. Right? So you could also, let's see if we can do this. PDF 0.15 plus PDF 2. There you go. All right, let's take a look at the last one. Given that the first 30 super igniters successfully launch, is it reasonable to believe that the failure rate for super igniter is less than 15%? So, given that this happened, the first 30 were success, is it reasonable to believe that the super igniters aren't actually operating at a failure rate of 16%? Well, we want to look at our probability that the first 30 were successful. So that's 0.0076. Now, because that is so low, lower than usually the alpha we use is 0.05, because that is lower than our alpha, we have some evidence to support the fact that the super igniter has a less than 15% failure rate, right? So that the probability that 30 successfully launched is so small, less than 1%, we might think that the failure rate is actually lower than 15%. So that's a famous question from 2016. Your stats teachers should know it. You might do it in class. So now you have a little bit of a jump start on your stats teacher. We're going to go over some more problems together. We're going to take a look at these two problems, again, comparing binomial and geometric. So we're going to go back to our Pepsi example. Assume that 40% of the market prefers Pepsi. What is the probability now that 5 or 6 out of 10 randomly selected cola drinkers would choose Pepsi in a blind taste test? All right, so now we're looking for the probability that 5 or 6, which means we're just going to add the probability of 5 plus the probability of 6. Again, still a geometric, or sorry, binomial setting, because fixed number of trials, 10. Binary, is it success, fail? Yep, you either prefer Pepsi or you don't. Independent, each person is independent of the next. Fixed number of trials, 10. And the same rate of success for every person, 40% coming in. So we could use binomial PDF, or we could use CDF. I like to use PDF. So the way I would do it, second distribution, go down to binomial, PDF. Number of trials, we have 10. The rate of success is 0.4. The X value is 5. We're going to paste that. Then we're going to add it to the probability that you get 6. Second distribution, binomial PDF, 10 and 6. And we're going to get about 31%, which, yep, we got that right there. We could also do geometric. So again, assuming that 40% of the market prefers Pepsi, what is the probability that the first cola drinker to randomly select Pepsi in a blind taste test would be the 5th or 6th customer? So now we want to know what's the probability that the first success or the first Pepsi preference is on the 5th or 6th. So we're going to do the same thing, except it's geometric, because we want to know what's the probability that the first comes then. So second distribution, geometric PDF, what's the rate of success? 0.4. What's the value? When do we want our first success? On the 5th. We're going to paste it. We're also going to add it to distribution, binomial PDF, 0.4, 0.6. There we go. We're going to get about 8%. Super quick on the calculator. That's why I prefer the calculator. Let's take a look to see how CDF would work. So here's a question you might run into that has CDF involved. So remember, CDF is cumulative. So it's that probability and everything below it added up. Example, suppose the likelihood of Barry Bonds hitting a home run is 0.2. what is the probability he will hit 10 or fewer, that's key, home runs out of 30 attempts? So we want to know, is this a binomial setting? First of all, do we have success or failure? We do, right? He either hits a home run or he doesn't. Is it independent? Yeah, just because it hit a home run last time doesn't mean he's going to hit a home run this time, or vice versa. Fixed number of trials? We do. We have 30. And is it the same rate of success every time? Yep, it's 0.2. So this is a binomial setting. We would use our calculators. And this time we would use cumulative because we want to know what's the probability he will hit 10 or fewer. So 9 would work, 8 would work, 7 would work, all the way down to 0. So we're going to go here. Second vars. We're going to go to binom CDF. Number of trials is 30. The probability of success is 0.2. And the value is 10 or fewer. It's going to be about 97%. Over here, same idea, except geometric. Suppose the likelihood of Barry Bonds hitting a home run is 0.2. What is the probability that he will hit his first home run within the first 10 times at bat? So again, within the first 10 indicates that's geometric. So we want to know what's the probability that his first home run comes the first, second, third, fourth, fifth, sixth, all the way up to the 10th. So we're going to use geometric, second distribution. Geom CDF. The p-value is 0.2. The x value is 10. And 89% is our probability. Now, sometimes it might be asked a different way, like right here. So again, the Barry Bonds situation. What's the probability he will hit 10 or more home runs? So 10 or more is 1 minus 9 and less. So that's why we wrote it like that. So I'm going to use binom again because we have a binomial situation. Why is it binom? Because we're given a fixed number of trials, right? We're given that 30 home runs, or 30 attempts, I should say. So once again, we're going to go to second. Well, first we're going to do 1 minus. So we're going to do 1 minus the probability that you get 9 or fewer, because we want 10 or more. So 1 minus, then go to second vars, binom CDF, trials 30, success 0.2, x value 9. Here's why 9, because if we put 10, then we'd be including 10 when we subtract. So we don't want to do that. We want to put 9 so that we only subtract 9, 8 all the way down to 0, and we keep 10 and above. And that's going to be about 6%. So the probability that he will hit 10 or more home runs in 30 attempts is going to be 6%. Let's see what that would look like on the geometric side. So example, suppose the likelihood of Barry Bonds hitting a home run is 0.2. What is the probability he will hit his first home run after the first 10 attempts at bat? So we're saying, hey, fail, 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 all the way up to 10 and above. So 1 minus, second vars, geom CDF. So the rate of success is 0.2. The x value here is going to be 10 because we want after his 10th. So not including his 10th, but after his 10th. 0.10. So that's going to give us a probability that he will hit his first home run after his 10th. All right. Well, hopefully that helped you out with binomial versus geometric. I will be back next week with sampling distributions for proportions. One of my favorite sampling distributions because I get to pull out my I have a whole bunch of beads that I use for this one. Please, please, please spread the word. Like I said before, this is much more valuable if you come to the live sessions because it gives me an opportunity to answer any of the questions that you have. Yeah, it's been Shane with Fiveable AP Stats. I'll see y'all next week. If you have any questions, email or let us know.